Hello students, Dr. Vance here. So let's continue our discussions on the properties of Laplace transforms. Okay, so today we're going to see some very unique properties. This one you can call them properties and also theorems. So let's see properties of Laplace transforms. Okay. You can also call this one some theorems. Okay, of Laplace transforms. Okay, so let's see about this one. We shall see three of them. We shall see here in these theorems. Okay, we have unilateral. Okay, so we have unilateral Laplace transform. Okay, so let's first see about the unilateral Laplace transform. Then later we shall see about the final value and then the initial value transforms also. Okay, so here, if you have Laplace transform x of what t, okay, such that it gives you, this one is called unilateral. Remember, we have unilateral Laplace transform, and then we have the what? So basically, this is more of a theorem than a property. Okay, that's why I call them what? Theorems. Okay, so we have the bilateral Laplace transform. Okay, that is the one we first started with. So bilateral Laplace transform is when here is what? Minus infinity to what? Infinity. That is what? Bilateral Laplace transform. But when here is 0 to infinity, then it's called what? Unilateral Laplace what? Transform. Please note this word difference. So the difference between the unilateral and the bilateral is that in the bilateral, we integrate from minus infinity to infinity. And the unilateral, we integrate from 0 to what? Infinity. Okay, here is what? X of what? T into e minus what? St the what? The t. Okay, so now if we have this one, okay, this is the unilateral Laplace transform. So please excuse me, I'm so sorry. I'll not write if here. This is the normal unilateral Laplace transform. Okay, this is the unilateral Laplace transform. And let me also write the bilateral Laplace transform for you. Okay, so the bilateral, that is the one we proved earlier on in the beginning of this particular Laplace session in signals and systems. So bilateral Laplace transform. Okay, so the bilateral Laplace transform is such that L t of x of what? T is equals to minus infinity to what? Infinity. Okay, x of what? T into e minus what? St d what? dt. Okay, this is the bilateral. But right now we are dealing with the what? Unilateral. Right now we are dealing with the unilateral. So, but right now we are dealing with the unilateral. Okay, unilateral Laplace transform. Okay, which is Lt of x of t, which is equals to 0, and then here is infinity. X of what? T into e minus what? St d what? dt. Okay, and then so now if we have this one, then this is the unilateral transform. So now if I have x of t, which has a Laplace transform of what? X of what? S. Okay, then if I have dt of x of what? T, it should have a Laplace transform, okay, of what? S x of what? S minus x of what? 0. Okay, so this is the unilateral Laplace transform. So I'm going to prove it. Okay, so now let me prove this one. Why it is so? Okay, so now to prove this one, what I do is that I have this particular equation. Okay, this equation. Okay, how do I get this equation? This equation can come by what? Differentiation, because you can see that here we are what? Differentiating. Okay, we are differentiating. Okay, so now let me write the normal Laplace transform equation. Okay, the normal Laplace transform equation. Let me write that one. Then from that one we can do our differentiation. So this is a normal Laplace transform equation. Okay, so here I can have, so let's say that I have, instead of x of s, I'll write x of what? T, which is actually equals to, here, unilateral. Okay, so here x of what? T, okay, into e minus what? St. Okay, st. Okay, so I have this particular equation. Okay, so let me differentiate both sides of this equation. Okay, so differentiate differentiate uh, differentiate differentiate both sides of this equation. Okay, so let me differentiate both sides of this equation. So if I differentiate both sides of this equation, I'll have d on what? dt of x of what? T. Okay, here is equals to unilateral, so 0 to infinity. Okay, d of what? The t into x of what? T into e minus what? St d what? The t. Okay, so basically this is what I can do at this particular stage. Okay, so this is how I can differentiate this one. Okay, so if I differentiate this one, then what I'm going to have is that here what you can do is that you can just use the what? The UV rule. Okay, the UV rule. So the UV rule you take here as V. Okay, and you take here as what? U. This is U. Okay, this is V. But please, my V includes my D of what? dt. Okay, so this is my U and this is my V. Okay, so now if I have this one, then what I can do is that if I use the UV rule, then I'm going to hold this one and I'm going to differentiate this one. But whenever you are differentiating something of what? Infinity, integration, this is integration, this is differentiation. If you are if you are integrating, so I'll hold this one. So if I hold this one, I'm going to have minus what? St. And then I have to integrate this part. Okay, so this part there's integration here, there's differentiation here. So if you are integrating, then you're going to get what? X of t. Okay, you're going to get x of t. Okay, so here is what? 0, here is what? Infinity. Okay, then the other part, okay, here minus. So now the other part, I'm going to differentiate this guy. If I differentiate this guy with respect to the t, I'll get minus s. So minus minus, then this will become positive. Okay, so I'll get what? S, and then I'll get s, and then I'll get this guy himself. Okay, then this guy also, this place, okay, this place also, I must what? Integrate it 2 times. Okay, integrate it 2 times. Okay, so now if I integrate it the 2 times, okay, if I integrate it 2 times, then I'm supposed to actually have, okay, so if I do the first integration, I'll have what? X of t. Like here, you see that when I did the first integration, I got what? X of t. So here to here, if I do the first integration, I'll get of x of t. Then I'm supposed to do what? Another what? Integration. Okay, so the second, and because I'm supposed to integrate it what? 2 times. So after the first integration, I'll get what? X of t. And then this is the second what? Integration, which I'm supposed to do. So that one is what? X of what? X of t. And here, if you differentiate this guy, you get s into e minus what? St dt. Okay, dt. All right. So basically, this is what you're going to get over here. This is what you're going to get over here. So now, from here, what I can do is that let me introduce in my limits. So if I introduce my limits here, here will be what? E exponent what? Minus infinity, which is 0. And then which will be what? 0. Okay. So that one will make the whole thing what? That one will make the whole thing what? 0. Now if I put 0 here, it will be e exponent what? 0, which is what? 1. And here will become what? 0. Okay. So I'll have what? The first one. If I put infinity here, I'll get what? 0. That will make the whole of this place what? 0. Now if I put 0 here, I'll get what? E exponent what? 0, which will be what? 1. And then here will become what? 0. So minus, because it's the lower limit. So exponent what? 0. Okay, plus this place. Okay, so basically you see that this place I have what? I have s, and if you check this thing very well, you see that is a what? It's equals to the it's equals to x of s, because it's what? Laplace transform, okay, of x of t, which is what? X of s. So here is equal to x of what? S. Okay, so now basically this is what I have. So now if I should rearrange this one, then you see that I have what? S x of what? S. Okay, minus what? X of what? 0. So is this simple? Okay, now here we are going to have d over what? Dt. Okay, into x of what? T is equals to what? S x of s minus x of what? 0. Okay, so basically this is the what? This is the proving that we need. Okay, this is the proving that we need. Okay, so we'll go to the next theorem. Okay, so let's go to the next theorem or property here. Okay, this is called the initial value theorem, or you can say property, but I think it's more of a theorem. Okay, initial value theorem. Okay, that's how it's properly called. So let's just stick to that. Okay, so here we're going to have if we have x of what? T, which is a Laplace transform for x of what? S. Okay, then if we have x of what? 0. Okay, then it's going to be equals to what? LT. LT means limit. Okay, limit as in function. Limit of x. Okay, of what? S. Okay, like this. Okay, limit of as s approach what? Infinity. Okay, so here basically this one is called, this place is called, okay, this one is called initial value of x of t. Okay, initial value of x of t. Okay, so now how do you prove this particular theorem? How to prove it is that we write the general Laplace, this equation. Okay, we write this equation, which is equals to, it's supposed to be x of what? S, but I replace that s by t. 0 and then what? Infinity. Okay, so d over what? Dt. Okay, so you see that I'm actually differentiating the x of what? T here. Okay, that means that I must also differentiate here d of what? Dt of this place. Okay, okay. So now this one, basically what I'm doing is that I'm just finding the Laplace transform for d of dt. I'm just finding the Laplace transform for d of dt. So the Laplace transform for d of dt is what? I'm finding the Laplace transform of d of dt into x of t. So whenever you're finding the Laplace transform, basically it is what? It is that particular function. If this function is what? X of t, then it's x of t, which is this one, x of t. Okay, if this is x of t, then x of t into what? E minus what? St dt. You see, this one is just like what? Saying that it's just like saying that x of what? T is equals to Laplace transform of x of t is equals to 0 and then what? Infinity. Okay, x of what? X of t into e minus what? St d what? dt. Okay, so in this case, if this place is differentiated like this, d of what? dt into what? X of what? T. Then this one becomes my x of t. So now I want to find the Laplace transform for this one. Then it will be equals to what? I'm writing 0 to infinity because of the what? Initial value theorem. Okay, here d of what? dt into x of what? T into e minus what? St d what? dt. Okay, so this is what I'll have. This is what I'll have. So now to deal with this one, I just have to differentiate and then introduce my limit. Okay, but one thing I have to be mindful of the fact is that here, see that earlier on when we did this thing, what did we get? Okay, you remember that in a unilateral Laplace theorem or property. Okay, when we had this one, we said that it's what? Is s x of what? S minus x of what? 0. Okay, so now this one. Okay, so now this is what I have. Okay, so now this one is going to be equals to what I have here, which is what? 0, which is what? Infinity and 0, d on what? dt. Okay, into x of what? T into e minus what? St d what? dt. Okay, so it's equals to this one. Okay, please let me just show you from here. Okay, let me just show you from here. You see that here, this is what I actually got. Okay, this is what I actually got. Okay, and that is why I've written what? The same thing what? Over here. Okay, so even with this one, okay, okay, how am I supposed to even end it? Okay, I'm supposed to even end it like that. The Laplace transform. Okay, here I'm supposed to bring. I'm supposed to end it that the Laplace what? Transform of what? D on what? dt of x of what? T. Okay, is equals to what? S x of what? S minus x of what? 0. Okay, all right. So you see that LTD of the t of x of t. This is what I got. So it's the same thing I've written here. So it's equals to this. But you see that here is the what? Initial value what? Theorem. And I said that the limit as it approaches what? Infinity. So now here I have to introduce the limit here. Okay, limit LT limit as what? S approach what? Infinity. Okay, as s approach what? Infinity. Okay, so now if s is approaching infinity, then what I must do is that I must introduce infinity into this particular equation that I have here. So if I should introduce infinity into this one, that means that this place into infinity. Okay, e exponent minus infinity here, s approaching infinity. Then that means that e exponent minus infinity is what? 0. So that means that this place will go to what? This whole thing will go to what? 0. Okay, if e exponent minus infinity is 0, if this place becomes 0, this whole equation becomes what? 0. So that means that I'll have s x of s minus x of what? 0 is equals to what? 0. Okay, so that means that I'll have what? S x, okay, of what? S, this guy can go there, is equals to what? X of what? 0. Okay, so but so this is what I can have. Okay, so now what I can have is that x of what? 0, okay, is equals to what? S, okay, x of what? S. But as what? As limit, okay, as limit, s approaches what? Infinity. Okay, as s approach what? Infinity. Okay, so this is the what? The final value what? Theorem. Okay, this is the final value theorem. Sorry, this is the initial value theorem. Initial value theorem. Let's look at the final value theorem. Final value theorem. So the final value theorem says that if x of what t has a Laplace transform of x of what s. Okay, then x of what infinity. Okay, we'll also have a Laplace transform. Okay, we'll also have a Laplace transform as s approach infinity. So let me say here, we also have a Laplace transform as limit s approach here, not approach infinity, sorry, approach 0, okay, of s of x, x of what s. Okay, so now let's see how we can actually prove this one. Just as before, which was called the initial value of x of t, this is the what final value, okay, of what x of t, okay, of x of what t. Okay, so it is called either the final value, or so it's called final value, okay, or steady state value. Okay, so it's the final value of x of t, and popularly called the final value or steady state what value. Okay, so now let's see how we can prove this one. Okay, so to prove this one, we're going to have a Laplace transform of differentiating x of what t, which is d of what dt. So Laplace transform of this one, which is equals to, here is final value. Okay, so we use a 0 to infinity, the unilateral Laplace transform. Okay, so here is x of what t into e minus what st d what dt. But I'm differentiating here, so I'll differentiate here into what dt. Okay, so let me just write it again. So lt into what d of what dt into x of what t is equals to here infinity and here 0. Okay, d of what dt into x of what t into e minus what st d what dt. Okay, basically that's what you get. Okay, so but this one, when we were doing the unilateral Laplace transform, this place is equals to what s x of what s minus x of what 0 is equals to this place. So infinity and 0 d of what dt into x of what t into e minus what st d what dt. Okay, so that's what you get there. Okay, so now if you have this one there, what we do is that we have to introduce our limit. Okay, introduce our limit. And what is that limit? So to introduce a limit, let me rewrite it again. The space is too small. Okay, x of what s minus x of what 0 is equals to what limit lt. Okay, as s approach what 0. So please note the difference. Note the difference in the initial value. I introduce the limit s is equals to what infinity. In the final value, I introduce the limit s approach what 0. In the initial value, s approach infinity. In the final value, s approach what 0. So if s is approaching 0, in this particular case, 0 to what infinity, d on what dt into x of what t into e minus what s what t d what t. Okay, so let's see how best that we can actually deal with this one. Okay, so now if we should have this particular case, then here it becomes what 0, and then it will become what 1. Okay, and then here what we're going to have is that we'll be left with this particular aspect. Okay, so if this place we have e exponent what 0, then e exponent 0 is what 1, so this place will become 1. So basically I have what s what x of what of x, okay, minus x of what 0 is equals to what limit. I've introduced this one, so I'll be left with what 0 and this one, and then d on what dt x of what t. So what happens is that whenever you differentiate and you integrate at the same time, you'll be left with that particular component alone. So here it will become what? X of what? Of t. And then I'll have my limit. What are the limits? Here infinity and here 0. So here I can bring x of what? S minus x of what? 0. I'll be left with this one. Okay, so if I'm left with this one, then what can I do? Okay, I can just put in the limits. I can just put in my limits. So if I put in my limits, then I'll have x of what? Of s. Of s. Okay, so of s. Here x minus what? 0. Okay, is equals to, if I put in infinity, the upper limit first. So x of what? Infinity. Okay, minus x of what? 0. Okay, so now this one and this one will cancel each other. So I have x x of what? S is equals to what? X of what? Infinity. Okay, x of infinity. Okay, but here as this one approach what? 0. So now x of what? Infinity is equals to limit as s approach what? 0. Okay, s x of what? S. Okay, so this one completes my work here. Alright, so those are the three values. Okay, the unilateral Laplace transform, the initial value theorem, and then the final value theorem. Thank you so much. See you in the next lecture.